More vectors then, step 2, 2011, question number 5. It's also question 2 from the step 2 support module for vectors. Got two vectors A and B. There are position vectors. They look a bit like this, I guess, maybe. And then we've got the point C, which is a reflection of the vector B in the line OA. So there's the line OA. So B is reflected over here to be like this. And then we need to show that we can write this here. So how do we do this? Well, we can come up with the vector across here from C to B. And that's clearly B minus C, right? Because it's minus C plus B to get from that corner to get to that corner. And now we can say, well, let's consider this point right there. I can get to that point in two different ways. I can either go some amount along the A vector, let's just call it KA, or I can go C plus a half of B minus C. It's a half, of course, because this is a line of symmetry. If it's the reflective line, so it's clearly a half either side. And of course, as soon as we set that up, we'll just expand out and move across, and we'll just get 2K here, which should be our lambda. So now we just need to figure out where this exact value comes from here that they're telling us about. And of course, dot products all to do with, perpendicular and angles and things like that. What kind of angles do you have here? Well, B minus C is clearly 90, is perpendicular to this A vector here. So we've got B minus C dot A equals 0. The dot product is distributive, so you can say that's B dot A minus C dot A equals 0. And now we can substitute in this result for C into there and do some more distributing. And then once we collect things up, A dot B is the same as B dot A. 2K is the thing we were looking for. That's just lambda. And so therefore, that is going to be our lambda right there. We're going to do exactly the same thing again to do this one, right? So D is the vector that's a reflection of C in OB. So there's the reflection line. C gets reflected, goes over there somewhere. D is over there. Just do the exact same thing. So C to D is going to be D minus C. We can come up with a journey to this point here. It's either some amount of B or it's going to be C plus half of D minus C. So that's going to be, I'm using another K. It's a different K to what there was before, I guess. K is easy to type, so I just use K. Anyway, we can expand this out and collect together, and we can throw the result for C that we've already got in here as well. And then we can do some more collecting together, and we end up with, or we just write the same line twice. Why not? Once we double everything out and move stuff over, we'll end up with something that looks a bit like this, I hope. And that seems about right. Yeah, because double than the 1b from here when you double it is over there, so it goes, yeah, that's fine. So we get D is this thing here, which is perfect, except I now need to show that mu is this thing here and what it is like in terms of this. So again, same thing again. We're just going to say D minus C dotted with B this time is going to be 0. And we've got a couple of results to throw in here. We've got to throw this result into here, which will look like this. And we've also got to throw this result into here. Just be careful with the minus minus to make that a plus. And now again, dot product is just distributive, so we'll just distribute. This collects together to make 2 lambda, and this B can go in there to make a plus 2 instead. And okay, now we can just simplify some stuff up. We can throw the result for this lambda, that lambda result we had before. We can throw that in there as well. And I've also divided everything by 2 here. So I've divided everything by 2, but then you get another 2 here from this 2 here. So I hope that all makes sense. And now, of course, this on the top is going to be A dot B or squared. And I think I can just rearrange this, right? Put this on the other side, A dot B or squared, and then divide by B dot B, and then just take away 1. And we'll end up with this is K. And our lambda, the mu that they're telling us about needs to be 2K plus 1. So let's times this by 2, and then add 1, and simplify it one last time. And we'll get mu is this thing here, apparently. Okay, so we've got all that down. Given A, B, and D, are collinear. So that means they're in a straight line. So A to D is a straight line with B passing through it. So I've just drawn B a bit too big, but it should be A, then B, then D in a straight line. Now the only, and find the relationship between lambda and mu, first. So the only thing we know about a straight line is that, say the vector A to B, no, we're now pretending B is here and A is here. So the vector A to B is just minus A plus B, or B minus A. A to D is of course just D minus A. And those two things, if A, B, and D are in a straight line, this one here is just some multiple of the other one, right? You take B minus A, and you just multiply it by some number, and you get D minus A. So we can write that in. Again, I'm using K. It's a different K to what it was before, but just want to be confusing, don't I? That's what you want to do. So we just have this. Of course, D, we can write in this result from mu and lambda. And now we can just compare A's and B's, as we often do in vectors. So 1b over here equals k mu, and that's it. 1 equals k mu. And comparing A's, we have minus 1 equals minus k lambda minus k. From here, if we times everything by minus 1 and divide by k, we get this. And we can just throw this, well, if we divide this by k as well, we can then just set them equal and get lambda plus 1 equals mu. And that's the relationship between lambda and mu. In the case lambda equals minus a half, determine the cosine of AOB. So if lambda is minus a half, that of course means mu is a half, which is very helpful. The cosine of AOB. So, I mean, we can throw these two results into our two formulas here and see if that helps. They look confusing right now. Cosine, now that of course means we're talking about A dot B equals mod A mod B cos theta, right? That's the only place we're going to get cosine from. Now, we haven't discussed moduluses at all in this question. However, there's a really useful result to remember here, which is mod of A squared is equal to A dot A. And that's because if you imagine a vector like this and you dot it with itself, it's going to be 1 times 1 plus 2 times 2 plus 3 times 3. What does that sound a lot like? Well, it sounds a lot like 1 squared plus 2 squared plus 3 squared, which is how you would work out the modulus of this vector, as long as you then square it to get rid of the square root. So this must be the same as this. So we can rewrite this for cos theta as this, and that looks very familiar. It's right in this one, isn't it? It's right in there. So what I can do is I can add 1 to both sides here to get 3 over 2 and divide by 4 to get 3 over 8 equals this business here. So therefore cosine squared is equal to 3 over 8, and square root both sides to get plus minus root 3 over 2 root 2. Now, how do we know whether it's plus or minus? And this took a little while of looking, but the only information we have here is that lambda is minus a half. And if we go back up to here, if lambda is negative, A dot A can't be negative because of this. So that means that we've got to have A dot B being negative. So A dot B is negative for this to work if lambda is minus a half. And looking over here, again, these things aren't negative. So therefore, if A dot B is negative, cos theta is negative as well. And therefore, it's the minus version of that. And the very last part of this question, I didn't understand what it was even asking me to do until I read the mark scheme and just saw that literally all it was asking you to say was, if lambda is minus half and mu is a half, just go to this formula here and put them both in, you get this. And therefore, D is the midpoint of A and B. That's all it's asking you to do. I thought it was actually asking us to calculate where A, B, and D were, but I just didn't understand how you're supposed to do that. But this is all you're supposed to say, which is a bit weird and dumb. But anyway, that's the end of the question. Thanks for watching.